So our last video, we left off here at position 4, where we're testing for subcooling. Again, subcooling is the gauge temperature minus the actual temperature of the refrigerant, which gives us subcooling. As the refrigerant liquid leaves the condenser, it runs into a liquid line, or through the liquid line, going over to a dryer. Now, some units will find dryers on, some you won't. The industry is really bad about, on residential applications, when to use a dryer and when not to. There's really no problems with using dryers until they get clogged and they slow down the flow of refrigerant. But they do take moisture out and debris, and they're a good thing to have in your system. But we'll cover dryers in the future. It continues past the dryer to the metering device. The metering device, again, is the item that, along with the compressor, separates the high pressure side of the system and the low pressure side of the system. This is what drops the pressure in the system. So this, let's say 300 psi, 85 degree refrigerant liquid hits that metering device. The metering device does what it says it is. It meters the amount of refrigerant running through it. In this case, it could be a piston, capillary tube, or a TXV. It sends liquid 80% and vapor 20% into this small little section of tube between the coil and the metering device called the distribution tube. So this 100% liquid, as it passes through the metering device, it gets reduced in pressure and just allows a little bit through at a time. It ends up being about 20% flash gas and 80% liquid, because it expands immediately. It's going into a larger item or a larger tube. As it flows through the evaporative coil and air from inside the home, normally considered wet bulb, which is a moisture temperature, the return air from where it goes through your filter and then goes to the system, it blows across this coil, and its job is to change the liquid refrigerant back to a vapor where it started at. The liquid refrigerant runs in, and liquid refrigerant, R410A, boils off at around 40 degrees. So that means as long as the air that's in your home and blowing across that coil is at least 40 degrees, it will cause the refrigerant to change a state or to boil off into a vapor. And that's why we use refrigerant, this type of refrigerant, or something we could cool our house with water. Do the same process with water, but this is more efficient because anything over 40 degrees changes the refrigerant. So as the heat from the air in your room passes across that coil, the hot molecules or the warm molecules, any molecule over the temperature of, say, 40 degrees, is going to jump off onto that coil. The air conditioner does not put out cold air. It actually accepts the heat from the air already in your home. The heat wants to be attracted to cold. So that coil's 40 degrees. The heat wants to be on a cold surface, so the heat molecules transfer from your air to that pipe, changing the temperature of the refrigerant as it runs through the system. And in doing so, it removes the heat from the air, and then you have cool air blowing out on the other side. This process, and figuring this out, is called superheat. So if you were to put a gauge right here and a temperature probe, you can determine, or you could put it over here, you could determine what your superheat is. Now, most companies do not manufacture units that use superheat to determine if it's working or not. And the reason why is if you have capillary tubes or a fixed metering device or piston, it works fine with superheat. It's actually a more delicate way to figure out how the system's working. But most systems now use a TXV, a thermal expansion valve, and that you cannot use. If you have a thermal expansion valve, you cannot use superheat because it fluctuates constantly. You have to use subcooling, which is on the other side of the system. And that's why subcooling exists, is because superheat does not work with the thermal expansion valve. As the refrigerant, which is now a vapor, leaves this coil, it is now a low pressure, low temperature vapor. The temperature of the vapor, say, is 55 degrees. If it went into this evaporator at 45 degrees, their difference is, say, 10 degrees, you have 10 degrees of superheat. Exactly kind of the way you did it over here on the condensing coil. It just uses different numbers. So again, when we're going to look at this gauge over here, now we're talking about low side pressure. So again, if the evap coil pressure on the outward side of it is at 125 psi, let's say, that puts the coil at about 42 degrees, the refrigerant, about 42 degrees. But if your thermometer on the pipe coming out of the coil reads 52 degrees, that's 10 degrees of heat that you added to this refrigerant. Where did the heat come from? It came from the heat in your home. The air moving across that coil, the heat changes the temperature of the refrigerant. So again, a gauge here that reads 42 degree temperature pressure coil, and a thermometer that reads 52 degrees gives you 10 degrees of superheat, which means it's doing its job. If you don't have this superheat or subcooling, it's not working. It's just refrigerant running through a system. So when it's through at that point, this refrigerant continues to make its way through the evap coil, through the suction line, it's what we call the line going to the compressor, and runs over to the compressor to start this cycle all over again. Again, this is like a wheel. It's constantly moving as long as the system's on. There's really no starting, no stopping point, but obviously since power is being used to make the compressor run, without power the system is not moving, is not turned on. So again, this is the low side of the system from the left-hand side of the compressor between mark A and mark C, or point A and point C. Everything on the left is low pressure, everything on the right is high pressure. And that gives you your cooling system. There's a lot more to this, but in basics, these are the four components and how they work.